So the last lecture, we look at the pFEM version of the finite element method. And well, we started looking at what happens with monomials. Remember what happened is that as we increase the polynomial interpolation order, we said that all those functions start to look alike. And that was not a good idea, right? Because then if you introduce a higher order polynomial, you said, well, it would be nice if at least that new function that I'm introducing to the basis can represent new behavior. But if we just use monomials, as you can see here, those functions start to look very, very similar. And so that had the associated problem that the stiffness matrix became ill-conditioned. And so we said, well, let's not use monomials. Let's just use orthogonal polynomials. And orthogonal polynomials have this very nice feature that, well, if you multiply two of those polynomials and integrate them in the domain, they are either 1 or 0 depending on which polynomials you choose. So they are orthogonal, right? And so the idea, we said, we're going to keep my linear basis functions, right? And then now we're going to hierarchically add new high order functions. And we said, well, we can add a quadratic function, and then we can have a cubic function and so on. But again, they are hierarchical. And being hierarchical is actually great because it's like you don't modify your functions, and you can also reuse a lot of that information to compute high order polynomials. So it's something. So in a let's say in a smart implementation, you will try to cache those computations so that you don't have to redo them, right? And so we define some function. We call this function phi hat, and the idea of that function is like they are not really the legendary polynomials, but those functions are defined in a way that their derivatives are the legendary polynomials themselves. And we do that because, well, in the stiffness matrix, we actually need the derivatives of the polynomials and not the polynomials themselves, right? So if you see this has a nice property that if you integrate the derivatives within the domain of integration, which again we define between -1 and 1 because we're always going to be doing quadrature in that domain, then this integral had this Kronecker delta property, so it's either 1 or 0, depending on whether the function is the same or not. Okay, and this had the greatest advantage that you get the best condition number for the stiffness matrix. And you will see how incredible this is in the project, because in the first exercise I ask you, compute the condition number and then draw some conclusions on that. And so finally, the shape functions look like this. And this is basically the functions we are going to be using for our 1D implementation. And well, after that, we said, well, the implementation-wise, it doesn't really change much from pFEM, right? So we still express our trial function this way. It's just that now this phi matrix or phi vector has high order shape functions. We just stack them behind the linear functions. That's the only thing we do. But we decided that we're going to keep the geometry linear. It doesn't make sense to have a geometry that was a quadratic or high order. And by the way, there was a mistake here, so thanks for pointing this out. This was actually yeah, there was a mistake there. So this is actually the Jacobian dx dx. And so, well, we looked at an example, and so we also started to talk a little bit about what is the meaning of the degrees of freedom when we're using pFEM, right? In pFEM, normally we associate a degree of freedom with the physical meaning of the displacement or the temperature, so the primal field at the location of a node. Well, in pFEM, that is no longer the case. We said we can only associate a physical meaning to the linear degrees of freedom because we know that those are still basically representing the displacement or the temperature. Remember that all high-order polynomials, if you remember this plot, all the high-order polynomials basically are exactly 0 at the end nodes. And so because of that, we can still assign a physical meaning to the linear degrees of freedom in pFEM, right? And then we look at an example of how to compute the stiffness matrix, and then, well, we see that it is really no different than what we did in 1D. It's just that now we have more terms to compute, right? So our matrices, our local stiffness matrix is going to be larger, and we gave an example a few minutes ago. If you have a cubic polynomial where your element is going to result in a 4x4 stiffness matrix. Okay, but this is pFEM in 1D. In 2D, things are drastically different. And the objective of today is to try to understand or try to have a glance on what is going to become pFEM in 2D. Yeah?
One question on the 1D case. What does the U factor as an outcome represent here? Is it the same as in pFEM, that because you have those higher order shape functions, does their displacement, do you only take, for example, the 3 nodes that are actually related to the linear shape functions in a element case? Or?
Okay, so we said that the physical meaning of the displacement can only be attributed to the linear degrees of freedom, right? Okay, well, and that is the reason for that, as we said, is that the linear shape functions are still the same shape functions that we use for pFEM, and all nonlinear shape functions are 0 at the location of the node. So at the nodes, we still get the physical meaning of the displacement or the temperature. Okay, well, but if I want to compute the displacement somewhere inside the element, right, then I have to evaluate the full expression. So my other degrees of freedom have no physical meaning whatsoever. Okay. And we said, well, maybe they could be attributed to high order derivatives, and we have an example of how we did that, right? Yeah. But in essence, we cannot, in these more advanced formulations, we cannot really assign a physical meaning to degrees of freedom anymore, right? And the same happens with these enriched finite element formulations where, the physical meaning is lost. And if you really want to get the temperature or the displacement or the primal field value, then you really need to evaluate the whole expression, okay?
Yeah, but we need to do that, right, in our problem. We need to,
Let's move on. We can discuss it later, okay? Okay. So, let me start by showing you what would look like some quadrangular element in 2D. Whoops. So now we have this element that has coordinates -1, 1 here, and then 1, 1 here. So it's a 2 by 2 element. This is going to be my coordinate C, eta. And this element is going to map to some quadrangular element in physical space. Let's do it something like this. Right? This is node 1, 2, 3, 4. 1, 2, 3, 4. Okay, so this would be our bilinear quadrangle in 2D. Yeah. So as we do always, right? We have the shape functions are going to be represented inside this element, and well, somehow we're going to choose some sort of mapping for the geometry, right? So we're going to use in the case of a bilinear, the geometry is going to be the same, right? So again, in the sense of isoparametric mapping formulations, your field is going to be linear, bilinear, and the geometry bilinear. But now that we're going in pFEM direction, then we're going to keep our geometry representation linear or quadratic at best, so that we can represent curved edges in 2 dimensions, right, in the physical space. But now our shape functions are going to increase to any arbitrary order polynomial that we want. So that is the objective. Yes. Yes. It's basically the same thing I just said, right? I'm just rewriting what I just said a few seconds ago. Oh, so the problem is my handwriting. I see. Yeah. Okay, similarly as before, we pick shape functions on the master element and for the geometry mapping, right? Okay, well, there are actually two spaces that we're going to look at. One is a so-called trunk space, and we're going to define what this means. Trunk space, and we're going to say, well, this is going to be TS for trunk space, and then of a given polynomial order P, and of course valid on omega, and this is going to be spanned by the following monomials. And then we have Ci eta I. Sorry, it's like this. I, and then for I, zero, 1, all the way up to P. I plus J is equal to 0. P plus C eta if P is equal to 1. And C to the power of P eta and C eta to the power of P for P greater than or equal to 2. This is one space, and of course I will show you a little bit with the Pascal triangle how those look like. And then the other space that we're going to be looking at is that the tensor product space. And this is actually a space that gives you a little bit more freedom, because you can actually choose the polynomial interpolation order depending on the direction that you want to high order, right? So you can think of, for instance, problems where you want a high order interpolation in one direction and a lower interpolation order in the perpendicular direction. So this space allows you to do that. So basically it's defined as S, PS for product space, and then pick C, P eta, just to signify that you can actually choose those independently, and it's spanned by Ci eta I and then okay, and let's go back to the I want to borrow this figure. This is a Pascal triangle. And it's just to show you how those spaces are looking at. So you see that for instance, everything that is orange here is my trunk space. Everything that is blue is my tensor product space. So you see that the tensor product space is very straightforward. So this is P equals 1, which is the same as the bilinear element. And then this one is here PS 2, 2, so a quadratic in C and a quadratic in eta. And then this one here is a cubic one. And so you see already that there is, it's very interesting because you don't keep complete polynomials anymore, right? It's like it's increasing towards this region, right? A complete polynomial would be something that this is a complete polynomial, right? And if I take this would be a complete polynomial of order 5, right? And that is not happening with the tensor product space. And that is what this trunk space is trying to fix. So if you look at the trunk space, well, for P equals 1, we get the bilinear element that we use in pFEM, the same. But now, if you look at what happens if we go to our trunk space 2, then it looks like that. And then for 3, it looks something like this. So I'm trying to keep my polynomials to get some sort of complete polynomial in place, right? And then this last one is like this.
Does that mean that the trunk space basically fills the how do you say it, function space with all the missing polynomials that we missed with the tensor product space?
Well, clearly, you see, for instance, here, this is my tensor product space of order 3, right? And then if you look at my, this would be my trunk space of order 3. Yeah? So I'm trying to get more the terms that are on the sides of the Pascal triangle. Now, keep in mind that we are not really going to use monomials. This is just an illustration of what are the terms that are going to be incorporated in my shake functions, okay? Just an illustration so that you have an idea. And again, remember that we always try to keep all polynomials up to a point. We try to form complete polynomials, otherwise, yeah, our basis is not good enough. We cannot really represent low order behavior. That doesn't make much sense, okay? So keep that in mind as well. Okay, well, in fact, the trunk space is more often used than the tensor product space. But as I said, you can think of problems where you may want to give a higher polynomial interpolation order in one direction as opposed to another. For instance, in fluids, you have these boundary layers, right, that need to be captured. And you can think, okay, I'm going to, along this direction, I'm going to increase the polynomial interpolation order because I really want to capture a high gradient in this region, but I don't really need to capture that in the perpendicular direction. So this may be one example where you can choose the tensor product space. But still, the trunk space is more often used. Yeah, so trunk space is used more often than the tensor product space. Okay, all right, but now we are going to look at shake functions. How do we build the shake functions, okay? Because as I said, this is just an illustration of what terms or how do we get our pFEM to account for the monomials in the Pascal triangle. So you know that a quadratic or a cubic interpolation should have those terms if you happen to use the tensor product space. Okay, to build the shake functions, we consider 3 types of functions. We're going to have first the nodal shake functions, which are also called vertex modes. And these are the same functions as in pFEM or standard FEM. Yeah, so the functions look like this. So the eth function as a function of c and eta is equal to 1/4 1 plus c c multiplied by 1 plus eta I eta. So here ci eta I is basically just the coordinate of the node in the master element. Basically saying that if I look at my original mapping here, right, this is my quadrangular element, and I look at this first node that has coordinates -1, -1, then I come here and I plug ci is going to be -1, eta I is going to be -1, and so my function is going to be phi1 is equal to 1/4 of 1 minus c multiplied by 1 minus eta, right? If I look, for instance, at a function that is for this node 3 that has coordinates 1, 1, then I come here again. Phi3 is going to be 1/4 of 1 plus c, 1 plus eta, okay? So this is just a compact form to write 4 shake functions. But again, these are the same ones that we use in pFEM. So our pFEM bilinear quadrangle is the same in both pFEM and pFEM. And the reason is, again, remember that when we go to pFEM, we are hierarchically improving our approximation, but we don't modify the low order shake functions. So that is the idea, okay? Okay, so these are the first functions. Then we have the edge, also called side modes. And you may already think, well, what is that? Who has an idea? Yes.
The ones that link to other elements.
Correct. So, contrary to the 1D case, where all the shape functions were basically 0 at the location of the nodes, right? Now, there are functions that are going to link between elements that are going to be non-zero at the edges. So these are called the edge modes. So you can think of these as, okay, I'm going to have this mode is going to be non-zero on this edge, but then it's going to be 0 in all other edges.
This is to ensure continuity.
Yeah, and we have to talk about that a little bit because it is not straightforward to ensure continuity, and we're going to see why in a minute, okay? So, there are p-1 edge shake functions. Please.
I can recall from my continuing class, my bachelor's, that this is always a little dangerous, at least the thesis said so, because this also can disturb the kinematic admissibility of the function, right?
Yes.
Be careful with it.
We have to be very careful not to have a non-conforming discretization, and we'll talk about that, okay? Okay, so let me read what I wrote. There are p-1 edge shake functions associated with each edge, and they vanish at all but one edge. Okay, this is, for instance, for if we take one edge, then the shake function is actually very, very straightforward because we're going to use already something that we know from the 1D case. So remember that nice function that we defined, that the derivatives satisfy this Kronecker delta property when integrated, right? We're going to use that to build our edge shake function. So in one direction, we're going to use that function, and in another direction, we're going to make that linear so that the product of the two fulfills this property that the function is only non-zero along one edge, okay? So phi I at Si, so at that edge, C eta is going to be equal to 1/2 1 minus eta, and then phi hat I of C, and this is I equals 1 all the way up to P, and you already know what this function phi hat is, because this is the same function that we were using in 1D. Is 1 divided the square root of 2i minus 1, and we were using this property that we could build this function using the Lagrange polynomials hierarchically, right? Yeah, so very straightforward. This function is going to be nonlinear in which direction? C, right? This is the guy that is going to become nonlinear. And if you notice, here in eta, linear. That basically says that, well, when eta is going to be equal to -1, this term here is equal to 1. When eta is going to be 1, this term here is going to be 0. So you see how this function for the first edge, which is this guy here, right, is going to go linearly from there, right? But then in the other direction, in the x direction, we are basically allowing a nonlinear function. So that is my first edge function. So along this edge, I can have a quadratic function, a cubic, quartic, and so on. Arbitrary order. Now, obviously, when I go to that edge, what happens in that edge? Yeah, they have to flip, right? So I have to make sure that in this direction, whatever function in that direction it has to be equal to 1 here and 0 here, right? And then I allow for a nonlinear function in that direction. So basically, these are flipped. And so that is basically going to be controlled by this term here. And this is going to be just simply phi hat of C or phi hat of eta. Yeah?
This works pretty well with quadrilateral elements.
Yes.
How do you do this with triangular?
Yes, we don't do it in the lecture, but if you look at the book, there is also a way to do that, and it's a little bit more tricky, but it can be done, and I have some examples in the book. And actually, I'm gonna also paste here the shake functions, but we basically can reproduce the same. And in the book, we're not using Legendre polynomials. I'm using Chebyshev polynomials, which is another type of orthogonal polynomials. But we discussed a little bit about this in the book. Okay, and finally, we're going to have the so-called internal or bubble modes. Yeah, there are p minus 2, p minus 3 divided by 2 shake functions of that type in the trunk space for p greater than or equal to 4. And also, if we look at, for instance, the tensor product space, there are also bubble functions, and there are, I'm going to just write it here, for the case of S tensor product space peak C. Remember that we can make this independent p eta. We have peak C minus 1, p eta minus 1 for p greater than or equal to 2. Yeah, so as you recall from the Pascal triangle, right, we see that obviously the bubble functions are going to be dealing with the center of the Pascal triangle, and so we would expect the tensor product space to kick in earlier, and indeed that happens for p equals 2 already, whereas for the trunk space we only have for p equals 4. But let me show you a little bit how these functions look like, so we have a better idea. So I'm going to come here, I'm going to copy this plot. And they look like that. So we have these three groups, right? We have the nodal functions, we have the edge functions, and we have the bubble functions. You don't need to take photos because you'll get these notes, huh? You get the notes. Okay, so these ones are the same as in the 1D case. Same, sorry, as in pFEM, that's what I meant. And now we have the quadratic ones, right? Notice that we have that quadratic nice function that we defined for the 1D case popping up in the edge, right? Then we have the cubic ones, the quartic ones, and for p equals 4, as we said, well, we already have our first bubble function, right? And then we have the quintic ones. Now we have two bubble functions, and of course we can continue, but yeah, the page is only so wide, so I could not draw more. Yeah?
Why are there only bubble functions at 4 and 5?
Sorry?
Why is 4 the minimum to have bubble functions?
Where is the bubble function? Why?
Yeah, why? Like,
Well, look at my trunk product space here. My bubble functions are going to be in this zone, right?
Yeah.
So the first one that looks at this function is there.
Yes.
Yeah? Okay. I would also copy the cubic ones, just to have them here, just because I have them in the book. But you notice we get a similar thing, right? We have the same functions that we use in the linear pFEM, right? And then we have quadratic functions. Keep in mind that now my functions are different. So I'm using Chebyshev polynomials, and I am not using the Chebyshev polynomials so that the derivatives are going to be satisfying that relationship. I'm just using Chebyshev polynomials as my check functions, and that is what you get if you do so, right?
Derivatives of the Chebyshev polynomials are orthogonal.
No, the Chebyshev polynomials are orthogonal for the construction of these check functions. Now, of course, you can work it out so that you use the derivatives being orthogonal, but for this case, it's just to show you that we get a similar type of pFEM implementation where we have quadratic functions along the edges, and then we have cubic ones, and then here we have quartic and the quintic, and now you see that the bubble functions start to show up for the case of a triangle for p equals 3. You have a question?
It was because of that.
Yeah?
I was wondering why does it start showing at 3 if it's still we're working with the same Pascal's triangle, the same type of function?
Because this is no longer the trunk space as we discussed for the quadrangle. It's a different space. But there is a trick here, and you talk about a little bit about nonconformity, right? So if you look at, for instance, let's go back to the quadrangular element, and now say I have two contiguous elements, right? And then this element for p equals 2, and then I put another element right here, and that is also going to be p equal 2, right? Do we have a problem there for the quadratic function? No, we don't. We don't have a problem. Why? They are both quadratic. They are going to be both continuous, right? They are going to match. But now, let's say I take this element. This is a cubic one. It's no longer a symmetric shake function along the edge, is it? No, it's asymmetric. So then if I put an element right here, yeah, they can be flipped, right? Depending on the numbering of the nodes and so on, right? The mapping is going to, maybe it's going to be flipped. And that can lead to a problem where we come up with a pFEM implementation where we have a non-conformal discretization. And so it may happen that along one edge, you have this function, and then it just happens that the neighboring one looks like this. And that is going to be non-conformal. Okay, well, you have to be able to deal with this in the implementation. So normally, when we deal with this type of problems, we try to figure out a way so that we enforce that we have a conformal discretization. And it is very simple to do this here because we simply take a function, and given some rule, we multiply that function by -1, and then basically we're flipping the function along the edge. Okay?
Yeah, but if it was correct at first, how can you realize?
Sorry?
If it was in the right way at first, they were both the same function, right? And you said that you multiply it by -1. Then
Yeah.
you get back in the issue.
No. You multiply one of them by -1.
Yeah, but if at the beginning they're already following each other.
If they follow each other, there's no problem.
Yeah, how,
If there is,
how beforehand?
yeah. So there are these rules. So for instance, normally in the implementation we have some sort of lexicographical order rule, and we say, well, I'm going to make sure that always along the edge, I take the first node to have the minimum number, right? So say you have this edge 10, 20. Those are the nodes of the edge, right? Okay, well, if for this shake function my node is 10, 20, then I don't do anything. But if it is 20, 10, then I just flip, and then I'm going to multiply that function by -1. So we can solve the problem using this lexicographical order is called. So let me write that down very quick. I cannot continue writing here, so there is a problem. So let me try. Apparently, Notability is not allowing me to write more pages. Crazy. Okay. So in the actual implementation, be careful of non-conforming discretizations. Due to odd shape functions. Okay? There is something else we have to be careful about. Okay, let's see this. Well, say there is a case where this is p equals 3, p equals 2, p equals 2, and this is p equals 1. Somehow you manage to basically assign different polynomial interpolation orders to different elements. Can we do this?
Apparently, yes.
Yes, we can. We just have to be careful what to do along
The edge.
the edges, right?
That probably means that the edge of the lowest polynomial dictates the shape function of the higher one.
Well, actually, you can choose either way. You can have the maximum polynomial or the minimum polynomial. So that's why I'm going to write here. We have simply two rules. You take just the minimum rule, which is the minimum of P1 and P2, or you have the maximum rule. Yeah. And we talk only about the field, right? Again, the field is going to be the sum of shape functions multiplied by their associated degree of freedom, right? But then we have to talk a little bit about what happens with the geometry. And as we said, well, mostly we're going to keep our geometry either linear, where x is going to be simply just taking my, again, I'm looking at the bilinear element here, not the triangle, right? So where this guy here is the coordinate, of node I, and here phi is my shape function. It's the bilinear shape function, right? We can actually have a quadratic mapping where now I'm taking, for instance, not only the linear but the linear and quadratic functions, and so now I have I equals 1 to 8 phi, right? And well, having a quadratic interpolation is going to allow me to do something that looks like, for instance, curved. Something that looks like this, for instance, right? But it is also possible to have different types of mapping. If there are cases, for instance, where you want to represent exactly certain type of geometry, well, in their book, Sabo and Babuska, they discussed you can actually do that by the so-called blending functions. And you can use this to represent, for instance, an arc of a circle. For instance, in general, particular geometries, circles, etc. But if you recall, we talked a little bit about this, and there is a problem with the use of this approach, right? We discussed this a bit. The moment that you are no longer using a subparametric or an isoparametric formulation, and your geometry somehow has a high order representation, you have to be a bit careful with this, these issues that are introduced, right? Artificial stresses in your formulation. So I don't think this is a problem if you want to represent part of your geometry, right? There's going to be some error there. But if everywhere your geometry is represented with high order interpolation, then you can have these issues. Yeah?
I have two questions. Can you go a bit up? Why for the maximum rule don't you represent it with B2 and B3?
Oh, it's just, I'm just looking at the two polynomials at one side or the other side. So,
B3 is
so
higher order?
here P1 and P2 are not cubic or quadratic.
Okay.
They are just looking at the two orders at one side or the other.
Oh, I see.
Okay.
And for the quadratic, isn't it such that you can also, what's the difference between doing a quadratic mapping geometry and a bubble shape function?
Well, the bubble shape function is quartic. And remember this, we want to represent geometry here, right? And the bubble functions are not really representing anything regarding to geometry because the functions are zero along the edges.
Right, but it's still representing the...
Yeah, but not at the edges. What you want is to be able to represent interesting geometries through the edges, right? The edges are the ones that are defining the geometry of your mesh. Yeah? Okay, but we still have to cover the issue of non-homogeneous boundary conditions, and this is going to take me a bit. So let me finish, and then we go for the questions. Okay. Because this is an important issue in pFEM. And it is an issue that happens in practice. What happens now when your boundary condition, your Dirichlet boundary condition along part of your domain, a boundary is non-zero, right? Let me try to grab again. I'll grab this plot here. Well, now I'm looking at a case where I'm trying to prescribe a Dirichlet boundary condition along gamma d, right? This is going to be, I don't know, some high order polynomial, some function. And well, if I look at my master element, this is where my element edge is. Okay, well, in the case, if we had Lagrangian shape functions, the prescribing Dirichlet boundary conditions there is very straightforward, right? If then, well, maybe I copy. Going to have, this is my node 2, this is here is my node 3, and then I have a node here 6, 10, 14, and say that the function that you want to prescribe looks something like this. It's a nonlinear function, and those are the nodes. Right, so this is my U bar, what I'm trying to prescribe. Well, I can write that U at 1 eta, so basically along this edge here, is going to be equal to phi2 evaluated at 1 eta U2 plus phi3 1 eta U3 plus phi6 U6 plus phi10 U10 plus phi14 U14. But now remember, these are very simple Lagrangian polynomials. And do you remember what was the nice property of the Lagrangian shape functions? What was the nice property? They have these. No. They have a partition unity property, but that's not the one that I'm looking for. The other one is the so-called Kronecker delta property, guys. Kronecker delta property. So basically, if I take this guy here, I know that only phi6 is equal to 1 there, and all other functions there are going to be 0, right? The same for all other functions. So that is a nice property of Lagrange shake functions. So then I take, for instance, the first, at that first node, then I get phi2 of 1 eta naught u2 is equal to u2 is equal to u bar evaluated at eta naught. It's very straightforward because I know that only that shake function is equal to 1. So this whole thing here, evaluated at that location, is equal to 1. Okay? And I have the same for the other one. Eta 1. The other one is phi3. u3 is equal to u3. Yeah? And the same. So enforcing Dirichlet boundary conditions with Lagrange shake function is very, very straightforward. Actually, it is exactly the same as everything we have done so far. Okay, but now we are dealing with a p-hierarchical implementation. So if we use now p-hierarchical functions, now we know that that property is lost. That is only conserved by the linear functions, okay? Well, we can write the same. We have 1 eta, and we can have phi2. This is exactly the same one as before. Remember that we are augmenting on the bilinear shake functions. So these ones here are my linear vertex modes plus phi6 u6 plus phi10 u comma eta u10 plus phi14 u14. These here are my nonlinear edge modes, right? Well, in the case of this function here, this is basically phi hat 2. Remember, it's a quadratic function there as a function of eta, because again, this is for p equals 2. For this one here is my phi hat 3 of eta, p equals 3. And this one here is my phi 4 hat of eta, because this one here has p equals 4. Okay, well, if this is the case, now it gets very, very tricky to do this, how to prescribe the non-zero boundary condition. So there are two ways you can do this. Maybe there are more, but I discuss in the book there are two ways. One is to do interpolation at Gauss-Lobato points, right? So we basically take the coordinates of the Gauss-Lobato quadrature rule and we evaluate those. So we say, well, u1 comma eta I is going to be basically u equals to u bar eta I. So we evaluate the whole thing. And then, well, we evaluate that for all the points along the boundary, 0 all the way to 4, right? And then that is going to give us 5 equations, right? Actually, it's not really 5 equations. It's actually 3 equations, because we know that the linear ones are independent from the rest, right? Since we know the linear DOFs, we solve for a 3 by 3 system of linear equations. And then once we know the values of the degrees of freedom, we proceed as usual. Yeah? So keep in mind that this is a local problem, right? At every edge where we're prescribing a non-zero boundary condition, we do this. We solve a very, very, very small system of linear equations to determine what would be the degrees of freedom that correspond to higher order shape functions. And once we know those, we proceed as usual to solve the whole system. Yeah?
But like we just said as well that degrees of freedom with the higher order shape functions, they don't align, right? There's no
Yeah.
physical meaning to those. So how can we have a prescribed condition coupled to?
I'll show you in a minute.
Okay.
Let me finish and I'll show you, because in the book this is explained much, much nicer, and there is an example. Okay, so the second approach is just do an L2 projection of the functions that I try to impose, right? Say gx, gy, on the space of edge functions. So the idea here, and I'm just going to just tell you briefly about it. The idea is that now you have some function that you're trying to prescribe, and then you write another function that is going to be an error function, right? And then you try to minimize that error. So if we look in the book, we have this interpolation is basically going to give you to a system that looks like this. And that's what I'm saying, that you do have to solve a system exactly because of that, because these all functions are interconnected in a way, right? So we have to solve that linear system. But this is the way it looks in practice. And again, it's a 3x3 system simply because for this particular example, well, we actually know the linear functions, they are decoupled from the rest. So we can know a priori those guys. We know those degrees of freedom, right? Here they are. And then for the high order ones, we solve this, we obtain these degrees of freedom here, and once we know them, we proceed as usual. And the other one is basically a projection on the space of edge functions. So the idea is kind of straightforward. We have a function that we're trying to prescribe, right? And then, well, if you remove the linear part of that function, which is basically what happens if you connect these two nodes, if you remove that, and we remove that because, well, the linear functions, again, are very straightforward to get, the degrees of freedom that are associated with those, well, we get a nonlinear function, right? And then we can define some sort of error function, right? Error function is going to be my u tilde, which is basically this nonlinear function, minus what we are trying to, what we can approximate. This is going to be our error, right? And then, well, we can define some sort of L2 version of the error, an L2 projection, that if you apply the derivatives, you can minimize this function, and you minimize this L2 projection, and that leads again to a 3x3 system that you have here, where again the idea is we obtain those generalized degrees of freedom, and once we know them, we can proceed as usual. So it's already 53 minutes. So let's stop here and then we go for questions. Or you have questions up to this point? Yeah.
Yes, related to this.
Yeah.
In 1D, we didn't cover non-homogeneous boundary conditions, right?
No, but because there is no problem in 1D. In 1D, remember that all the nonlinear functions are exactly zero.
Oh, yes.
So in 1D, there is no problem. The problem is only in 2D. Okay? All right.